Hello, this video is on section 2.2, which is called Some Rules for Differentiation. In the last section, we learned the definition of the derivative and the limit process that calculates derivative functions for us. And you may have noticed that that is a bit tedious. We will use that when we need to, but the hope is maybe we only need to do it a few times and we start to notice patterns. So that limit definition will kind of fade into the background once we start remembering some patterns and shortcuts. So we're going to roll out a few rules here. There will be more rules coming up, but the rules in this section will actually allow you to take the derivatives of a very wide variety of functions. So our first rule is called the constant rule. And it says the derivative of any constant is 0. Right, and let's think about this. If we have the function f of x equals 4, its graph is just a horizontal line, always at a height of 4. Derivative measures slope of the tangent line. As I move along this graph, the slope of the tangent line is always 0. So the derivative is a function that is always equal to 0. And so it is the extremely boring function f prime of x is 0. So when we take the derivative of a constant, we get 0. It's technically the constant function and the 0 function. But if you just think of it as the derivative of any number is 0, that's going to be fine in context. Okay, now, next rule is called the simple power rule. This allows us to take the derivative of anything we can write as variable to a power. So here is the general pattern. If I am taking the derivative of x to the n power, so x here is our variable. Remember, this thing in front really just means take the derivative. If we take the derivative of a power of x, the derivative of that is n, whatever this exponent was, times x to the n minus 1. The way people think about this sometimes is I have x to the n, and we kind of think this n travels in front and gets subtracted by 1. And we'll see a bunch of examples in a second. I'm not going to prove to you why this always works. I'm going to show you one example, and then we'll just kind of buy in that all of the others can be proved. It gets very tedious. So this is where you probably just want to watch the one and then trust that everything else works out. And this proof here is a little bit tedious, so we're not going to have to go through all of the details. You're not responsible for, sorry, I'm doing this outside and there's some disruption. You're not responsible for writing down all of the details here. You just kind of have to understand where this comes from. So let's think about this. Let's suppose we have the specific function f of x is x to the third power. It's the function that cubes things. What would be the derivative of that function? So this is our most generic form. And f here is the cubing function. It takes its input and cubes it. So we have the limit as delta x approaches 0. Very specifically for this one, when we apply f to x plus delta x, that means x plus delta x cubed, and f of x is x cubed. Now, here on the side, let me just do a little algebra. So this is kind of a side calculation so that I can insert it later. I want to know what is x plus delta x cubed. That means x plus delta x times x plus delta x times x plus delta x. If I FOIL out these, I get x squared plus 2x delta x plus delta x squared. Now I'm going to have to use the distributive law. So first I'll take x times all of these things. And I would have x to the third plus 2x squared delta x plus x delta x squared. Then I would take delta x times all of these things. And I would get x squared delta x plus 2x delta x squared. I hope you're not copying all of this. Plus delta x cubed. And if I group my like terms, there's x to the third. Here I'll notice I have 2x squared delta x And here is one copy of x squared delta x, so that makes 3 of them total. Here I have x delta x squared. Here I have 2 copies of x delta x squared, so that makes 3 of them. And then finally at the end I have delta x cubed. So let's just go back here. That was all just so that we know what this is equal to. So we have the limit as delta x goes to 0 of x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. This is very tedious, which is why you want to absolutely just remember the shortcut to the answer. If you need to do this every single time you do a calculus problem, it's going to be a nightmare. What I notice in this numerator is that x cubed and negative x cubed cancel. So I am left with the limit as delta x approaches 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed all over delta x. So I can factor out that delta x. I didn't quite give myself enough room. But in the numerator, everything is divisible by delta x, leaving 3x squared plus 3x delta x plus delta x squared. There's been a delta x in the denominator all along. The delta x factor of the top cancels with the bottom. And we have the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared. Finally, I can plug in. I am going to plug in delta x is 0. The x just stays in here. So we have 3x squared plus 3x times 0 plus 0 squared. So a lot of that is 0, and our answer is just 3x squared. So let's just take a step back and think about what we did here. Don't get caught up in the details. Just admit we took the limit definition of a derivative and very carefully did all of the algebra. But what we've really learned here is that if the function f of x is x to the third, then the derivative, the function that keeps track of the slopes of the tangent lines, was 3x squared. Go down here, 3x squared. So this is an example of that pattern. If we're taking the derivative of just a variable to a power, that power shows up in front as the coefficient, and then the new power is 1 less than the original. So the power comes in front and gets smaller. This would work with any power of the variable. So let's practice this. If you can write something as a power of a variable, then you can apply this rule. Now, writing something as a power of a variable might require using some exponent rules where you're a little rusty. Rules about fractional exponents, rules about negative exponents. So let's do an easy one together and then hit pause. Well actually, for the Edpuzzle video, I'll probably prompt you to do some of these. So here we have f of x is x to the 4th power. So to take the derivative, get in the habit of labeling things. If you're taking the derivative of f, write f prime of x equals. If you just have unlabeled formulas, in any kind of problem with complexity, you'll wind up confusing yourself. So our exponent here is 4. That's going to come in front. 4 times something. And then we have x to the 3rd power because that's 1 smaller. Okay, try this one. What do you think g prime of t is? Follow that pattern and try to type it. So g prime of t, the 9 now comes in front, and the new power is 8. It gets smaller by 1. Right, now let's look at this. We have to process this as a power of x. Our calculus rules are very powerful, but sometimes they require things to be written in a very specific form. So think to yourself, what power of x is this? 1 over x can be written as a power of x. what is the exponent? So I hope you remember these rules that things in the denominator are negative. So this is really x to the negative 1 power. So our derivative here would be negative 1 times x to the, and here's where we want to be really careful. The new power is what we get by literally subtracting 1. So we had negative 1 and we are going to subtract 1. So this is negative 1 times x to the negative 2. And depending upon the context, you might be able to get away with just leaving your answer like this. But we're going to be using derivatives to answer problems. And if you don't really know what this means, you probably won't be able to finish the problem. So let's remind ourselves. X to the negative 2 means 1 over x squared. And probably the nicest way to write this whole thing is just negative 1 over x squared. Or some people would put that minus in front. Negative 1 over x squared, either way. But really get in the habit when you're dealing with these exotic exponents, make sure you know exactly what they mean, because if you don't, you're going to be able to abstractly take the derivative, but then not do anything with it. Right, here's another one that you may have forgotten. A square root. A square root is a power of x. Which power of x is a square root? Here you might remember it's a half power. Right? Roots are fractional powers. So the rule still applies. So when we're taking the derivative, that power 1/2 comes in front. It's now a coefficient. And our new power would be 1/2 minus 1. So this is 1/2 times x to the negative 1/2 power. And again, let's make sure we understand what that means. A negative power means it's in the reciprocal, and a half power means it's a square root. So I would write this like so. We're going to suspend the rule about radicals in the denominator because this is far simpler than any rationalized version. Okay, a couple more. M of z is z to the 4.3 power. Right, this is a rather abstract exponent. Maybe we'll just leave it as is. The 4.3 comes in front, and the new power is 1 less. And then finally, this last one. Right, this one is super easy, but maybe deceptive. X all by itself is which power of x? It is the first power. So our rule here would be 1 times x to the 1 minus 1, which is 1 times x to the 0. X to the 0, hopefully you remember, is 1. Anything to the first power is 1. So our answer here is 1. Rather than use the power rule here, I think this is worth remembering as its own rule. Right, so strictly speaking, you can get this by applying the other rule, but this comes up so frequently that it's just worth knowing. Assuming that we're working with a problem where the variable is called x, the derivative of x is 1. I would recommend just knowing this. Okay, so what are the rules we have so far? We know how to take the derivative of any constant. It's just 0. And we know how to take the derivative of something that is a power of the variable. It follows this very predictable pattern. Now we can start making things a little more flexible. So here we have the constant multiple rule. If f is a differentiable function of x and c is a real number, then if we're taking the derivative of c times a function, it turns out the answer to that is just c times the derivative of the function. So the idea is when you're just multiplying by a number, right? When you have a coefficient in front of a function and you want to know its derivative, that coefficient basically just stays there, right? We don't ignore it, but we don't really do anything to it either. We just leave it there to multiply what the derivative would otherwise be. Right, so let's look at a very quick example. If g of x is 3x to the 4th, then g prime of x. Right, here's how I would do this. After a little bit of practice, you're going to skip writing the intermediate step. I'm going to say, all right, 3 is just there hanging out. I'm going to leave it there. And then the rest of it is x to the 4th. So what's the derivative of x to the 4th? It is 4 times x to the 3rd. And then I just multiply these together. So my overall answer is 12 times x to the third. I'm really just taking the derivative of x to the fourth and then multiplying it by 3. Let's be very clear, this only works when we are multiplying by a constant. This doesn't work if we're multiplying a function by a function. Just if you're multiplying a function by a number, that number just kind of hangs out to multiply the derivative. So if we can write something as a constant times a power of a variable, we know how to take its derivative, but you do need to practice this. So let's look at this first one. I have f of x is negative 2 times x to the fourth. So my derivative would be negative 2 times, oh, I misspoke. I'm starting with negative 2 times x to the fifth. My derivative would be negative 2 times, well, whatever the derivative of x to the fifth is. By the power rule, the derivative of x to the fifth is 5 times x to the fourth. So this is negative 10x to the fourth after we simplify. Look at this example. This is written as x squared divided by 4. But can you think of how we could write this using multiplication instead? My hope is you realize it's the same as 1/4 times x squared. So the rule is still in play. I have a 1/4 here, and then I would multiply that by whatever the derivative of x squared is. The derivative of x squared is 2 times x to the first, which we don't really need to write. So when we simplify this, 1/4 times 2 is 1/2, and x to the first is just x. Let's look at this one. Again, see if you can write this as a number times a power of x. So you really want to just separate all of the things that are numerical coefficients that don't have an x in it from what's going on with x. So what you could do, right, and with practice, you might be able to do this all at once without writing out the intermediate step. I'm going to write this very clearly as 3/4, right? Fractions are numbers. It is the number 3/4 times 1 over x. And we'll remind ourselves that 1 over x is just x to the negative 1 power. Do this first, and I recommend literally having it written down. If you think you're doing it in your head, you're really rolling the dice as to whether it will work out. So now we've written this as a number times a power of x. So when we take the derivative, we can use the rule. That number, 3/4, is just kind of hanging out. And then the derivative of x to the negative 1 is negative 1 times x to the negative 2. And now let's make an effort to clean this up. So I have negative 3/4 if I multiply those numbers together. X to the negative 2 means 1 over x squared. So I have negative 3 over 4x squared. So how could you write the function k as a number times a power of 2? 4 is there, and square root is half power. So it is now set up so we can use our rule. It is 4 times whatever we would get from the power rule. 4 times 1/2 is 2. A negative 1/2 power is a square root in the denominator, so probably the simplest way to write this is 2 over root 2. Okay, a couple more. Here we will notice that this number 9 is not completely in front. We want to be able to write this so that the coefficient is the very first thing. But we can use the square root rule. This is the same as the square root of 9 times the square root of x. So this is 3 root x, which is the same as 3 times x to the 1/2. It is a little bit annoying, but if you want to use these rules, you have to take that effort at the beginning to write it, or at least imagine it in your head if you're very good at doing this intuitively, but that's risky. I would recommend write it down as a number times the power of x. And anytime you write something down, try to label it. M of x is. don't just randomly write formulas. So our derivative, right, I'm writing m prime of x is, I'm not just randomly writing a formula that's unlabeled, 3 times the derivative of x to the 1/2 by the power rule. The number is 3/2. This, again, simplifies to 1 over root x. So this is 3 over 2 root x. And then finally this one, let's just simplify what we have here. If we reduce the numbers, we have 5 and 15, which reduces to 1 over 3. If we reduce x and x to the third, they're both divisible by x, which is like 1 over x squared. So p of x is 1/3 times 1 over x squared. So we can write that as 1/3 times x to the negative 2. I do some work at the beginning so that I can write this as just a number times the power of x. So our derivative would be 1/3 times what I get from the power rule. Remember, we are literally subtracting 1 from the exponent. So if the exponent is negative, it becomes more negative. When we simplify this, we have negative 2/3. A negative 3 power means 1 over x to the third, and this would be our simplest form. You'll need some time to practice this so that this is really at your fingertips, but then it should be pretty easy. The kinds of things that you're doing here will not go away, right? Maybe not literally every day, but more often than not, you will be using something like this to do a calculus problem as we proceed through the year. So you want to practice these really well now so that you can do them without looking things up, so that you can do them without hesitation, because very soon this kind of stuff will just be a step in a longer calculus problem, and you don't want to be stuck trying to figure out this particular step. All right, one more rule in this section, and luckily it's very intuitive. So this is called the sum and difference rules. So here's the good news. If we are adding or subtracting functions, we get the derivative by just adding or subtracting the derivatives. So here it is expressed kind of abstractly. I have the functions f and g added together, and I want to know the derivative. Well, it's just the derivative of f plus the derivative of g. Just do them separately and keep the addition. Same with subtraction. If I am subtracting two functions, the derivative is just derivative of the first one minus derivative of the second one. I'm not giving you a proof here. Maybe it makes sense to you if you just think about how things change. You can trust me on this. There's a proof in the book if you really want all the details. So let's look at a very quick example. Let's compute the derivative of m of x equals 3x squared minus 4x plus 1. So here's what we want to keep in mind. Addition and subtraction really don't make the problem any harder. And constant multiples really don't make the problem any harder. So our derivative here, right, here's kind of what's going on structurally. That coefficient of 3 is just hanging out. The subtraction is part of the answer. The coefficient of 4 is just hanging out. And the addition is part of the answer. So let me try to color code things. Here's 3, here's 4. They're just kind of in the answer waiting to multiply things. I have my addition and subtraction. Then we just fill in the individual derivatives. So here, this is x squared. Its derivative is 2x to the first, which is just 2x. The next thing is x. Derivative of x is 1. The last thing is 1. The derivative of any constant is 0. So I'm going to annotate this. Don't feel like you have to do this if you already understand. But this part here is the derivative of x squared. This part here is the derivative of x. This part here is the derivative of 1. So we have kind of these structural elements of, yes, there's subtraction, yes, there's addition, yes, there are some coefficients, but they're just kind of built into the answer. Here's my subtraction, here's my addition, here's a coefficient, and then I just fill in my derivatives. And then, of course, if we simplify this, our simplified answer would be 6x minus 4. Let me give you an enormous warning. This rule that we've just used applies only when we are combining functions by adding them or subtracting them. If we are adding functions together and want to know the derivative, we can do the intuitive thing. If we are subtracting functions and want to know the derivative, we can do the intuitive thing. This rule that we've just done does not apply to multiplication and division. There are rules for how we can think about derivatives when we have multiplication of functions or division of functions, but they're complicated and you haven't seen them yet. So just keep that in mind. If I am adding or subtracting functions, derivative rules are easy. If I am multiplying or dividing functions, derivative rules are a little bit complicated. So you're going to be practicing a bunch of these in your classwork. Let's just do one problem that reminds us of why we care about derivatives and one thing that's useful for them. So let's imagine the parabola y equals 3x squared minus x minus 1. I'm just going to draw a schematic diagram right now. And we can check that the point 2, 9 is on that graph. Let me see if I can switch to Desmos and just show this to you very quickly. So I believe it was y equals 3x squared minus x minus 1. And we had a point on that graph at 2, 9. Okay, so there we go. We have a parabola, and there is a dot at 2, 9. So suppose I want to know the equation for the tangent line at that point. What is this tangent line? Well, we can do this with calculus. So we know that the slope of the tangent line is calculated by the derivative. So our function here is 3x squared minus x minus 1. Let's take the derivative of this function. It's going to be 6x minus 1. Right? So I did this in my head, and hopefully you're going to get good at this soon. I have 3 times the derivative of x squared, which I know to be 2x. So in my head, I just said, oh, 3 times 2x is 6x. Minus derivative of x is 1. Minus derivative of 1 is 0, so I didn't even write it. Now, let's be really careful about what the derivative function does for us. So I'm going to write this out as a sentence just to reinforce it. The derivative is a function that keeps track of all of the tangent slopes. Right? That's one interpretation of what the derivative is doing. So we have something very general here. Now for this problem, we don't really care about all of the tangent slopes. We really only care about this one. So we really just care about the tangent line that occurs at x equals 2. So very specifically for this problem, at x equals 2, the slope of the tangent line would be f prime of 2. F prime of x is a general formula for finding slopes in a general way. F prime of 2 means what is the slope of the tangent line at x equals 2 for this particular function f. If we plug that in, we get 6 times 2 minus 1, which is 11. So we're still not done, but here's what we know. We know that for this tangent line, the slope is equal to 11, and we were given that a point is 2, 9. So let's just use point-slope form because that's easiest. So our equation for that tangent line would be y minus our given y coordinate equals slope times the quantity x minus our given x coordinate. So y minus 9 equals 11 times x minus 2. Let's switch to Desmos and see how we do. Y minus 9 equals 11 times x minus 2. And here we go, right? If we zoom out, we can see that clearly that green line is different from the red parabola. But as I zoom in, I can't even tell the difference. So almost certainly we have that correct. Okay, so there's a lot in this section, right? Just a few rules, but they're super powerful. And so you'll have a lot of time to practice these in class because, again, what you're learning here is a building block for almost everything else we do this year. So I want to make sure that you can do these very quickly and very consistently. And